This video was produced by
Welcome to the afternoon session of the Offshore Wind Track. Everybody's had their lunch, so we'll try to put some loud noises in here to keep you guys awake. My name is Brian Redmond. I'll be moderating today, and we have a great panel for the discussion. First, John Miles, a well-known Duke. John is a professor here at the Department of Integrated Sciences and Technology, and directs the Virginia Center for Wind here, which you, if you went to lunch, you saw the opening ceremony for that. John's been very instrumental in launching the offshore wind program here in Virginia, and has been doing some great work characterizing the offshore Virginia and looking at ways we can reduce costs, improve data accuracy, and he'll talk a lot about that today. Dane Zammit, also here from JMU, is the data manager at the Virginia Center of Wind Energy. Dane graduated with a BS in mathematics and physics from the University of Malta, and I've been to Malta, and it is very windy in Malta, so Dane comes well recommended. He's done a lot of work with John in characterizing the Suffolk and Chesapeake Bay Bridge Tunnel Coast areas where we're looking at putting in some demonstration turbines. And then finally, we have Guy Chapman from Virginia Power. Guy's responsible for developing of hedging strategies for Dominion's assets, marketing and trading environmental products, and Dominion's greenhouse gas offset effort. Guy is incredibly smart. He's probably one of the smartest guys working at Dominion, and he's got a tough job. He's representing environmental projects inside a utility that's primarily focused on thermal and nuclear energy. So he's a tireless worker on behalf of renewable energy here in Virginia, and specifically within Dominion. So with that, what I'll do is we're going to go sit in the front couple rows so we don't cramp our necks while we look at these presentations, and we'll start out with John, then we'll go to Dane and then Guy, and then I'll open it up. I'll put some questions out there to get the conversation started, and we'll open it up for questions from the audience. So please write those questions down and pass them forward, and we'll answer them.
Thank you, Brian, and I want to thank my other panelists as well for joining me today and giving you all a glimpse of some of the work that we've been doing and we've been doing with others as well to try to support and advance offshore wind energy here in Virginia. Okay, so the title of my slide is in fact the title of a final report that we are going to be submitting. We have already submitted drafts and discussed drafts, but I'll just give a little bit of background here. The project is Offshore Wind Advanced Technology Demonstration Site Development. And the presentation I'm going to give today describes some of the progress that was made during the year on this. This is a revised version of a presentation I gave a few months ago with my partners to the Virginia Offshore Wind Development Authority, which is a governor-appointed board that is intended to, in fact, facilitate and help advance offshore wind in Virginia. And I do want to cite here other individuals who contributed to this presentation. Rick Thomas from Timmins Group, who's in the room here. Tom McNeilan from Fugro Atlantic, he is not with us today. And Jay Tidlow, who is here but may or may not be in the room here. These are four of a number of partners who have been working on this project. Now, this was stimulated this was intended originally to position Virginia to attract private sector interest in developing a distributed suite of nearshore and offshore platforms. And the idea here was to be responsive to what we anticipated to be a call from the Department of Energy for projects that would test, demonstrate, advance offshore wind technologies in the U.S. Such a call, in fact, was released some months ago. There were 30 responses, and we'll all hear in the fall who was awarded, and we're hoping that there might be something coming to this region as well that would, in fact, lead to, as we like to say, steel in the water sometime soon. These are the sites, and I'll acknowledge Timmins Group here. This is their map, but these are the sites that, after careful consideration, it was determined would be appropriate locations, possibly in state waters where large, new, advanced offshore technologies might be tested. You'll notice the yellow site just south of Newport News. The notion there would be that a turbine may not be installed for operational purposes, but rather techniques for installing and foundations and such could be tested at that site. There's also the green area just at the other end of the Merrimack Monitor Bridge Tunnel, just north of Suffolk, and that is an area that possibly could be appropriate for an offshore wind turbine for testing. And then finally the red space to the north end of the Chesapeake Bay Bridge Tunnel. So those are the three study areas that were concerned. And specifically, the work plan was designed to further the mission of the VCIRC, or Virginia Coastal Energy Research Consortium wind team, to advance the economic viability of offshore wind, establish appropriate mechanisms for attracting industry, and as I said before, hopefully to be consistent with and in line with the priorities that have been set forth by the U.S. Department of Energy. And I want to acknowledge the entire project team. As you can see here, it is quite a formidable team. We've had a lot of different types of tasks and initiatives involved in this effort that I will describe as I go through here. And then as you're looking over here, you may recognize some names, and some of these individuals are here. I see Ann Flandermeyer-Kerwin in the back of the room. She's been an important partner here. Guy Chapman, Molly Parker-Plotz, these people are here and have been advisory and important supporters of the effort as well. But at the end of the day, what we really wanted to do was accomplish two things. Conduct what we would characterize as a pre-development effort to determine the viability of these three sites for these kinds of installations, and to conduct the appropriate science and measurements and analysis and modeling to determine a little bit about the wind resource, the water levels and behavior, the subsurface for foundations, and so on. So I outlined the tasks here. At JMU, we were responsible for overall project administration, documentation, management. Timmins, Fugro, utility professionals were essentially responsible for the siting assessments and evaluations, the pre-engineering analysis of interconnection options, and so on. Timmins also prepared quite a complete and comprehensive set of documents that would advise a later development in terms of the regulatory process and permitting. The wind resource, mid-ocean design environment was characterized. That was a combined effort between Old Dominion University, JMU, and Weatherflow. Outreach, relations, support with regard to the industry, supply chain participants, stakeholders of other sorts, led by Principal Advantage with support from Timmins and JMU. And we've also conducted a viewshed analysis and engaged in a variety of ways with all the stakeholders that were identified early in the process. And these were the assignments, really just sort of laying that out in a different fashion. So I'm going to just continue from there. Now, this is I have a URL here. I must apologize. Since I prepared this presentation a couple months ago, there's been some changes in terms of how our websites are handled. This is what I would characterize as a draft or, shall we say, experimental web page, and it is not accessible to the general public without a JMU VPN client. So it won't get you where you'd like to go right now, but what I can assure you is that at our main webpage, windpowerva.org, we will have a link to this site within weeks, and from this site to other online resources that are related to this effort. What we have attempted to do here in cooperation with the Department of Mines, Minerals, and Energy is stand up a new website that would support all of the different offshore efforts and provide a common hub for information related to work we're doing, other work that DMME supports and our partners are involved in. There's a link that isn't visible on this screen grab, but there is now a link to the VAUDA page where you can download information from their site, minutes, meeting minutes, meeting announcements, and so on. And one of the other areas that we've been very involved in, I should acknowledge James Wilson, one of my colleagues here, is not only identifying but carefully organizing all the vast array of data that are available that pertain to offshore. Now, I'm not a GIS or geographic sciences expert, but Dr. Wilson is, and he and a graduate student very meticulously have developed a structure that will be accessible by the web to get at these data. Many of them public data, some of them proprietary, but all important for development. Timmins, with support from JMU and from WeatherFlow, has developed two, we think, fairly user-friendly web tools that are going to expose anybody who's interested to information that has not been readily available before. This first one, the Map and Data Viewer, is a fairly straightforward set of layers where we have selectively chosen layers that are available publicly, but only the ones that would be particularly interesting to those who might be interested in offshore development. And if you look down below at Virginia Beach and then out to the right a little ways, there's your lease blocks as defined by the Department of Interior, where that we recognize as the wind energy area, the space that is most likely going to be home to our first offshore wind projects in Virginia. So you have the opportunity by clicking on these boxes to bring up all these layers that you see here in the legend and then some. You can scroll down and see more and start to get a feel for what the offshore world looks like. And it's a lot more complex than you'd think just by looking out at the open ocean. Likewise, we have stood up a wind, weather, and energy viewer. In my estimation, I think in Rick's as well, this is the really exciting page, because we hope it for some who maybe carry a somewhat simplified or simplistic view of the winds and the weather patterns off the coast. You look at some of the maps, in fact, the very map that we have at our Wind Center display out in the hallway, and you see colors, and the colors represent an average wind speed, and one might be inclined to think, well, great, it's always 7.5 meters per second all the time. And in fact, you'll now be able to visit this site, click on these yellow arrows, and look at wind data being measured instantaneously. Click anywhere else, including the lease blocks over on the right-hand side, and courtesy of WeatherFlow, look at model data within the hour that give you a real good sense of just how complex and variable, both in terms of space and in terms of time, the winds really are. And we have incorporated an algorithm as well that is hidden, but allows one to estimate within a given period of time across the year exactly how much energy is estimated to be available by way of wind power and what a sample capacity factor might be as well. So this is really the first of its kind that we have seen that provides to the general public access to these kinds of data and information off our coast, so the public can start to appreciate the challenges that developers have when they are trying to assess this resource. And you heard earlier, if you were in the resource assessment seminar earlier from a couple of different people, just what a challenge it is to get real data and to deploy instruments. There are other techniques for doing this, but the modeling at least helps and gets us a step or two further along. Now, I'm not going to spend too much time here. I'm going to show you some pretty pictures. These are slides courtesy of Mr. McNeilan and Fugro, who worked under subcontract with Timmins, and they did the very important analysis based on public data and proprietary data of the subsurface, below the water in the areas that we were interested, to try to get a sense of what would be required in terms of foundations and in terms of avoiding undesirable after effects such as scouring, and giving us the means to be able to make plausible estimates as far as what costs would be for installing these kinds of turbines. I don't have the expertise nor the time to get into the details. Tom gives a very nice presentation of these slides, but I just want to go through them so you can at least see some of the takeaways that he offers here without the benefits, of course, of his very detailed explanation. But the bottom line takeaway, at least from me when I heard him give this, was that it is not simple. We don't know everything we probably would want to know about the subsurface in these areas, but there are serious effects that could be realized by installing, and it would need to be done with great care to avoid undesired effects from installation in these areas. As you can see here at the CBBT site, scouring could be significant, but on the upside, a single turbine installed in an experimental fashion might give us a little bit of knowledge that would be applicable out in the deeper sea as well. So the notion here is to support efforts by the private sector, perhaps supported by the federal government and the state government as well, to learn by installing and testing and demonstrating in waters that are close to land. and trying to reduce the risk before we go much farther out to sea and where it becomes much more expensive. Again, I'm going to go through this fairly quickly here. They looked at the CBPT site. They also looked at the Suffolk and Newport News sites as well. And again, saw some concerns, maybe fewer concerns in the area of Suffolk, but other issues arose as well, as Timmons identified, with the existence of oyster beds and other factors that could play into permitting. So Tom also left us with some recommended next steps. And I'd envision that a company such as his or one like his would be engaged in some fashion were this project to move on to development and engineering and construction. Just to ensure that you remain oriented here, these are the three spaces that we focused on. We've got Rick here in the room. I can't speak in detail as Rick would, as he presented these slides to the VADA board. And Rick, you're welcome to stand up if you have any comments you'd like to make, but I just want to commend the work that Timmons did. They literally were responsible for about at least half of the entire effort here. And they went to great lengths to make sure that we thoroughly and very comprehensively characterized these sites, identified potential showstoppers, engaged with the authorities and the organizations and other stakeholders who would have an interest in any concerns about projects in these areas. They were responsible for looking at interconnection, looking at other technical factors and issues that could play into a project here, different options at in terms of how one might connect one of these turbines to the grid. As I said earlier, along with Principal Advantage and JMU, they engaged in a lot of conversation and discussions and meetings with the vast array of stakeholders who would have an interest and could contribute to the development of a project here. Likewise, they did a very exhaustive study of the regulatory process and the permitting options with respect to the federal and the state governments, and have produced a whole series of documentation that I think would be very valuable to a future developer of a project in any of these spaces. So our goal here is, if it's not clear already, all along, was to be able to present to the Department of Mines, Minerals, and Energy volumes of information that would reduce risk, reduce cost, and accelerate and facilitate project development in these areas. Is that a fair assessment, Rick? Moving forward here, I mentioned our partnership with WeatherFlow. WeatherFlow conducted quite intensive modeling and, in fact, is continuing to support modeling off the Virginia and under a separate contract off the North Carolina coastlines. Their modeling techniques so far are demonstrating that these kinds of approaches that apply very high-level computational modeling using data sets to set conditions, boundary and initial conditions, can be very valuable to learning more about the characteristics of the winds in areas where we just simply don't have sensors. So we understand better the complexities, and they have, I think, very wisely broken the year down to 8 subseasons of about 45 days each. And they're identifying what drives the winds in those areas, and can we break it down to the specific mechanisms that are more or less important in those subseasons, so that we can better forecast conditions, whether for installation, operation, performance, or construction even. So I know this is one of Jay's slides, and I know he likes to make the point that on the left-hand side you see the traditional AWS True Power map, and the colors are nice, and it's good to know on average where the winds are stronger, where they're weaker. That's a fantastic prospecting opportunity. But it doesn't tell us how much the winds actually change from hour to hour, minute to minute, day to day, how variable they are in terms of space and time. So we're hopeful that the information that we're gathering here by defining these subseasons and then examining the different contributions to the total resource, frontal passages, continental air intrusions, sea breezes, etc. I see at least one person up there, Lynn, shaking her head yes, and everybody else, I hope you're still with me. Once again, Jake would love to get into this, I'm sure, but we don't have the time, unfortunately. I'll acknowledge his contact information at the end. So they have so far produced 6 of the 8 subseasons and given us enough information to be able to appreciate the complexity, and within a couple months we'll have a full year analysis based on their models. Again, I'm going to just scroll through these, but again, his point here was just showing a time lapse here and demonstrating how quickly and how broadly the winds do change over time. And it's not just a matter of the farther away from land you go or the higher you go, the winds get stronger. In fact, you may have heard this morning it could be the opposite. The wind's actually going down as elevation increases. So we're trying to capture the essence of that complexity and be able to advise the development community now where they ought to be and some of the things they need to look out for and ways to take advantage of the strongest winds. We worked with Old Dominion University. They collected and analyzed many, many data sets, gave us the means to do the modeling by understanding how the data in fact is operating, mostly at lower elevations, but we were able to extrapolate upward, and that's the focus of Dane's presentation in a little bit. But with the data that they collected and the analysis they provided, we now understand within close proximity of real measurements what the winds are doing at these sites that are not very far from land. And that was important in terms of at least being able to characterize the areas that we're trying to study and provide recommendations for in this particular report. We also installed several months ago a 50-meter mast near the Suffolk site on the grounds of the Nansemond wastewater facility, which is a Hampton Road Sanitation District facility. That tower is near the bottom where it says 29 meters, pretty close to that area right there. And that data, the data is being collected there right now, and we'll continue to benefit from the collection of data at that site. And that is, of course, courtesy of our anemometer loan program here. I've just got a couple of WASP slides, and I'm not going to spend any time on these because I don't want to steal any of Dane's thunder here, but WASP and WindFarmer are very advanced industry-grade software programs that allow us to take real data, digitally model a terrain, a space, and then extrapolate from that data point to a region, and essentially construct a wind regime. And then once that's in place, we can install a turbine, install, of course, in quotes, install a turbine where we like and estimate what its performance would be, either over a year or over a shorter time period. But that's all I'm going to say about WASP and WindFarmer, and let Dane take it from there. And then finally, but certainly not least importantly, and in fact maybe most importantly, we designed and engaged in a very detailed, lengthy campaign to identify the critical stakeholders and have conversations, meetings, telephone calls, correspondence, letters, etc. with all of those. I don't list them here. It's a very lengthy list that will be available in our final report, but we felt it would be critical, and I think anybody who is experienced in site development, project development will tell you, and I know that the AWEA Siting Handbook reflects this, that if you're to look at a timeline of project development, communication starts at the beginning and ends at the end. And the same thing applied here. We didn't want to wait till the end and consider it an afterthought. We needed to know who was going to be interested in this kind of an effort and what their opinions were and what concerns they could bring to the table as well, so we could take those into consideration. And I lied. There's an incomplete but a fairly complete list of the organizations that we interacted with during the course of this project. And what our report reflects is the nature of those interactions and what we learned from those interactions. Finally, and I'm not at liberty quite yet to show these, but we have generated some visual simulations. I'm waiting for some permissions to demonstrate or to present some specific images, and that's all I'll say, but these are already populated with appearances of wind turbines on towers and how they would look from these vantage points on the CBBT and from some other angles at both sites as well. And then finally, I just want to once again acknowledge at least the 4 individuals besides myself who were instrumental to this project, provide their contact information here. And I think, Brian, we're going to save questions. I'll thank the audience. Thank you.
Why don't you...
John, why don't you go ahead and introduce Dane and kind of characterize how his presentation fits into this, because you probably have a better view of that.
Thank you, Brian. And you can go over to Dane's presentation. So there were just a few slides on WindFarmer and WASP. Dane had a number of tasks throughout the year, but he has a technical background in physics and is very well versed in software and modeling. And what we asked him to do was essentially build up the space near the CBBT site and then also near the Suffolk and Newport News sites, build those sites digitally, not only identify and collect, but then he had quite a fair bit of shall we say, massaging of many data sets to make sure that they were consistent in format with the needs of the software. And then we had the opportunity to take different kinds of turbines, different sizes, power curves from those, and then apply those to the models that Dane had built, and then go ahead and actually estimate what the performance of those turbines would be. Again, important in cost modeling and estimating energy output. Is that fair, Dane?
Well, thank you, John, for the introduction. I don't need to explain what I'll be talking about. I'll just really the finer details in what effort goes into building these models. So I'll be talking about the project overview, just my part really, what sites I modeled, where the data sets I used came from, and other details about the project. And I'll also go through the four major steps in model construction: building a topographic map, data processing and cleaning, mapping the wind resource, and finally turbine energy estimation. I'll also be showing a few of the results I came up with, and I'll finish up with some conclusions. So this is a map which you've seen during John's presentation of the regions we've been looking at. The orange stars represent turbine locations where I finally placed the turbines, and the red stars indicate where the data sets were driven from. So the CBBT site, I only used one data set off the Chesapeake Bay Bridge Tunnel. That was around 5.5 years of data from around 16 meters depth. And the turbine that was selected for this site was the NREL 5 megawatt reference turbine. From the Suffolk site, two data sets were used. One from the Monitor Merrimack Bridge Tunnel, which was about 12 meters deep, and another data set from the Suffolk site, which had three data sets from three sites, from 50 meters, 85 meters, and 97 meters. And that was a much shorter term data set of about 15 months. And the reason why I didn't model the Newport News site was because that site is not intended for energy production, so it's a bit redundant to model that. So the first step is building a topographic map, and the software I used was Global Mapper, which is a very convenient piece of software. It allows you to look for data sets online, download data layers, and what goes into building the map, the basic is elevation data in the form of contours, and mapping the terrain in the form of roughness polygons. And you can load these data sets online. So for a roughness map, you need land cover use, as shown on the map there. And basically you assign numerical values to different terrain types, and this will affect how the wind flow model and the software will calculate the vertical shear of the region you're attempting to map. And the image on the bottom right shows how the digital vector map will look on WASP. The red lines are the contours, while the blue and green are the roughness change vectors. Basically, that is what you need to map the wind resource. Before that, you need to process your data sets. And the Wind Farmer MCP module is ideal for looking at the data sets, making sure that the sensors were working ideally throughout the entire process. So let's say if there was a problem due to icing, you'd have a zero reading for like maybe a couple of hours or 3 or even entire day, and you'd have to make sure that that is not included in your data set, since that will introduce more uncertainty into your analysis. The basic outputs from the MCP, you can export the clean data sets to WASP as an observed wind climate file, and you can also produce wind roses, which gives you a basic overview of your wind resource from that Met tower. The next stage is to actually use the topographic map and your clean data sets in WASP, which is a tedious and long process. The first thing you need to do is verify your vector map in WASP, make sure that the roughness change lines do not intersect and they do not touch each other, because that will cause the model to run, will cause more errors. And the way WASP works is you generate using these data what is called a wind atlas, which basically for a search, which you can see in the bottom right there. So basically what it does, for a certain height and a certain roughness, you have a certain wind speed. So it kind of gives you a site-independent outlook of what the wind resource looks like in that area. And after you've done that, the next thing to do is to actually plot a grid of the site you are looking at, which are the last two images on the bottom left, and generate a grid, define a resolution, which I set to 30 meters. To get a more, a finer look at the wind resource. Yeah, I think the battery may be down. Can you guys hear me? I'll just continue. Okay, so can everyone in the back hear me? All right. So basically, the wind resource grid is basically a way to map your wind resource from the Met station where you have your data set, and you can vertically and horizontally extrapolate your data set up to the hub height of the turbine you wish to place at the site. And the reason why I covered such a huge grid area and not just homed in at one site was for two reasons. One, because at the time when I was producing these grids, the actual location of the turbines were still undetermined. And the second reason is that wind farmer, which is the software that I use to do turbine energy analysis, they use a method called the association method, which requires the wind resource grid to be projected over the entire area, including where the Met tower was. Thank you, John. So that was the reason. Okay, so finally, the fourth step was using wind farmer to actually project the wind resource and how much these turbines will produce over a certain period of time, usually an annual analysis. Now, one thing that I failed to mention in the introduction is that for the larger data sets, namely the Monitor Merrimack Bridge Tunnel and the Chesapeake Bay Bridge Tunnel sites, since they were 5.5-year data sets, I also used, based on the weather flow, how the weather flow divided their subseasons over 6-week periods over the year. So I also analyzed turbine energy output over 6-week period throughout the year to analyze differences between, let's say, how much energy kind of wind do they produce in January and February compared to, let's say, June. And that involves loading all the data sets, including the wind resource grid. So all the roughness change lines, the contours, the wind resource grid are loaded again into Wind Farmer. And then you can place your turbine. You can see the final location for the the Suffolk site over there. Since we used the Vestas 3-megawatt turbine, which data for is readily available online, we loaded that into the turbine information and ran the software. Here are some assumptions and uncertainties that I assumed. First of all, I assume no output losses due to utility downtime, icing, maintenance, and things like that, which certainly plays a role. I also assumed an anemometer uncertainty reading of 2%, model extrapolation of data from horizontally between 5 and 10% based on the site, how far the Met Tower was from the site, the turbine location. Vertical extrapolation, depending the farther away. This is something that was more guesswork from my part. I have found studies that indicate up to 30% error from data sets using just a single vertical data point. So I assumed 20% for data points that were far away from her turbine hub height. And the error in the wind flow model was determined based on model validation. Here are some results from the Suffolk site. Newport News had 3 model runs from 50 meters, 85 meters, and 97 meters, and they basically gave similar results, an average capacity factor of 27 to 29%, and net yield of 7 to 7.7 gigawatt hours, with an uncertainty of 25.1 to 31%. And this is because, as I explained, there is a high degree of uncertainty in vertically extrapolating your data set from, let's say, 12 meters all the way up to 90 meters with no intermediary data points. For the MMBT data sets, the capacity factor for annually was 22.4, so significantly less. And this is probably because, as I explained, there is high degrees of uncertainty with the limited data sets that I had to deal with. Another interesting thing Wind Farmer gives you is probability distributions of expected energy outputs. Mostly, these are called p-values, and I plotted them on a graph. What you can see is that they roughly give the same values. You know, the MMBT is the mean expectation value is less than for the Newport News sites. But as far as the Newport News sites, they gave roughly consistent values. And the result here is a table of results that I got from the CBBT. With CBBT, I'm showing the subseason analyses that I did, and you can see that there are some significant differences from one subseason to the other. So the best subseason gave an output of 40.4% from January to mid-February, whereas for subseason 4, which is in May, I believe, it basically half that. So this is just to highlight how important it is to know your wind resource, because energy production can vary significantly during the life cycle of a wind farm or just a single turbine. Yeah, and there are some results. Another thing that Wind Farmer does, it gives you the probability distributions based on, you can give a 1-year outlook, you can give an expectation value from 10 years and 20 years. And what you can see is that if you go for a longer term outlook, the uncertainty decreases a little bit. You get more certainty in your analysis. So conclusions, my results indicated that the demonstration sites may be suitable for energy production. Again, there are some uncertainty in my analysis, but initial results seem promising. Again, there's a high degree of uncertainty, mostly from the vertical shear estimates. Also, there are significant seasonal variation, which I attempted to address through subseason analysis. Again, and ideally, you'd have 2 or more anemometers at different heights. Let's say, ideally, you'd have data readings from 20 meters, 60 meters, and then you can project that up to 80 meters. An interesting study that I read during my, my studies is a mathematical technique called the method of least squares, which you basically take data sets from lower heights, because building 100-meter towers, especially offshore, is very expensive, and you use those data sets to generate a synthetic data set up at that hub height, and you can use that data set to do more reliable analyses. And I think that concludes my presentation.
Thanks, Dane. Turn it over to Mr. Chapman.
I think that was, I really appreciated Dane going through the detail of what happens in wind modeling. So I'm going to talk more generally about a cost of energy study that Dominion got some funding with from the Department of Energy. And in that, we're going to be going over a bunch of different areas. And what he showed you is just how much detail in each of these areas you go into. So that was just the wind, trying to resource assessment and wind modeling. When you're talking about turbine design or the foundation design, or looking at the details of trying to lift a 400-ton nacelle up in the air, you get into equal amounts of very specific detail. And so just kind of highlighted, gave you a window into one small portion of all the detail that has to happen in all these other areas. So which button? Okay. Well, a lot of people here earlier, I'm going to skip all the Dominion stuff, since I'm going to make the assumption you are all here in the morning and listen to Salou talk. I will talk a little bit just about what we're doing in offshore wind. You know, the call for information and what is really driving us to be interested in it. The call for information came out in Virginia from BOEM. And that really is one of the big drivers. I mean, we're having a great resource off of our coast. There's not many scalable, large-scale renewable resources off our coast or in Virginia. There's onshore wind, there's biomass, there's hydro, but all of them are relatively limited. So when you talk about opportunities for large-scale renewable development, that is one of the big drivers that actually makes us take this very seriously and kind of forces us is leading us into the work we're doing. We have, what I'll talk about today a little bit, is the Department of Energy grant that we are the principal investigator for, and I'll go over that a little later. And then some of the other things we've talked about on here are, I'll highlight later on, maybe 2 transmission studies that Dominion's done looking at the ability to interconnect offshore wind transmission into Virginia. And then some of the process that BOEM has gone through. Recently they've had requests for information on the commercial lease form, and then auction design, and also Atlantic Wind Connection has put out a request for right-of-way, which I think recently has gone forward in Virginia. This is just policy both on a federal and state level. I will highlight under federal in 2011, I'm going to go over a little bit talking about the offshore wind, National Offshore Wind Strategy, which a lot of the things that I'll be talking about are going to be driven from. And secondarily, recently 2012, the DOE call for information, and then the DOE grants for advanced technology development, which have just submissions came for in the end of May, I believe. This is what we're trying to work on. So we have a high cost of energy offshore, and we're trying to bring that down to be conventional. A lot of what's in there is a lot of risk premium, and that range is based on EIA information. I think EIA has just come out with some new information that actually moved. I was surprised. It looked like it moved it actually higher than that. And you're seeing what I would consider a lot of first of a kind premiums in those numbers. But what you've seen, this is an NREL chart really looking at the cost of offshore wind energy over time. It has gone I think the industry has tried to scale up. There's been a lot of constraints with supply chain. There's been a lot of risk allocation issues. People have learned a lot. People have lost money doing it. And then you see really it's starting to level out in the European projects. Although European projects now, the next set of them are going to be farther from shore. And some of our early, I think, early offshore wind projects in the U.S. in terms of dollars per kW installed seem to have relatively low assumptions. And I think people have trued those up. And some of the last slide, we had the PPAs for some of the existing projects that people were working that were showing them back toward the prices you get in Europe. So the Crown Estate recently just issued a report. The Crown Estate, that's basically the Queen owns the land 12 miles off of the coast of England, and so they're the ones that lease it. They've been actually a big proponent of trying to lower costs and get leasing going. They've released a report talking about cost reduction paths, and there's really a couple areas. I'm going to talk a little bit about technology, and technology is simple. When you're trying to do this, you're really trying to increase output or reduce installed cost. You get a lot more bang for your buck to get more megawatts out of the same install. So when you look at spending money and spending time and trying to get more efficient, you really get a lot more trying to work with your turbine manufacturer, getting larger blades, getting more efficient turbines. Because the other side of this is you can only as these things get bigger, you really can't take that much steel or concrete or people out of the process. This is it's a very asset intensive process. There's a lot of risk in it, and you can only squish so much out of the cost and keep safe, reliable operations. The two other big areas, which I'm not going to address today, but I think a lot of people are very aware of, is talking about supply chain, which is still developing in the U.S. and I think in Europe has been a big issue. And I'll give an example of a supply chain issue is transformers. There was one of the projects in the UK that we visited when we were doing some research had a transformer supplier go bankrupt. And so they were delayed while their transformer was in bankruptcy, and they really had mobilized assets. They couldn't get it out. So from a supply chain perspective, should you really procure 2 transformers or have a backup, and how much extra does that cost you? Those are the type of issues I think people are actively working on, and having a clear vision of how much volume is coming out is a key part of that. And the other bit is in finance, perception and management of risk. Who owns what risks in the project? Because right now, no one wants to own any of the risk. You have shipping people, you have people that do construction, offshore construction, and you have utilities, and a lot of them typically haven't had to play together. So there you have new working relationships that are not as well defined as maybe just building a typical generation facility. This is for those of you who have looked at the DOE's offshore wind strategy. This is their kind of pathway that they've laid out. Technology development, removing barriers. Some of those barriers are, I think BOAM has been working very actively with Smart from the start to make it easier. But when you're building something of this size, there's going to be a process that's going to take a while. You can't get around some of those issues in terms of planning, contracting, resource assessment, and permitting. You can try to smooth those down, but the big aim is once you have the big issue is once you have a huge demand, you're going to get through a lot of those issues. And then I think highlighted under technology development, innovative turbines, and marine system and engineering, really trying to integrate those to lower costs. So this is this graph really looks at what the Offshore Wind Accelerator, which is a group that was put together by the Carbon Trust, which is another UK entity, to help target lowering offshore wind. So the members in that Offshore Wind Carbon Trust Accelerator, you see on the right. So Dong Energy is the largest offshore wind constructor in Europe. E.ON's a very large European utility. RWE, Scottish Renewables, all those people are big players in offshore wind. And so it is I think it has about $30 million of funding from the UK government. Each of those entities have put in significant money. They work as they have a number of panels that drive where the cost reduction money goes. And they have run a number of kind of contests. So they're looking for, recently they talked about a kind of RFP where they're looking for people to bring in solutions for higher voltage inter-array cables, the cables between the turbines, to bring them in at 66 kV, which would have less losses. So they kind of target those areas and then try to run some type of market-based solution to get costs down. Their report recently came out with about $150 to $152, pounds per megawatt hour, was where their starting point is. So that equates at the current rates to about $230 to $240 per megawatt. Their target is to get it down to about 100 pounds per megawatt, which is about equivalent $157 per megawatt hour. The DOE strategy is targeting get it down to 100, and starts at 243. Now, European rates are much higher. Their electricity rates are a lot higher than ours to start out with, so that they don't have to come down as far as we have to come down in the U.S. to make it palatable. The second bullet here talks about our partners on our DOE grant. We're using an Alstom turbine, which is a marvelous turbine. I'll talk about it in a little bit. Moffatt Nickel is a marine engineering firm that is based, or they have an office in Virginia Beach. Virginia Tech and National Renewable Energy Lab. NREL is doing all our resource assessment and cost modeling. And Virginia Tech is doing much of the site characterization work for us. And our target, the DOE goal is to get to 10 cents per kW. Ours was to have a 25% reduction in cost. And so we really targeted those categories down there, larger turbines. The main area is trying to get increased capacity factor. And then we looked at some different ways to do foundations and installation together so you lower the net cost of all that. So this is a site assessment. The project is looking at basically 3 areas of projects. So we're looking in the Maryland wind energy area, at the Virginia wind energy area, and then northern North Carolina. The aim is to see if we can find a set of projects that basically could be served out of the same supply chain area, and have similar characteristics. So you could most likely use the same foundation design. So you use the same major foundation design and maybe have 2 or 3 variations you'd manufacture for some of the different depths within them, but they have similar design areas. So the mid-ocean characteristics for the design criteria is mainly nor'easters coming in, not Category 3 hurricanes. Once you get past going south past Cape Hatteras, you really have much more of a hurricane design area. So we've decided to look at 3. So we're going to look at from Maryland, Virginia, and northern North Carolina is in the bottom right. You can see the shipping coming out of Virginia Beach, which as it comes out of Virginia Beach, that red is more dense, yellow is less, and green is less. That little block that's in, kind of looks like a Lego block on the right, right below the red, which is a military area you don't want to traverse through, can't build in. That's the northern North Carolina site. So we tried to aim for a set of projects that could be phased, could have a lot of volume, and could be served out of Virginia Beach. So the first set of turbine innovations came through the Alstom Haliade. Is that, John, are you here? Is that the right way to say that? Haliade turbine. And so one of the big things is permanent magnet generators are big in all the newer turbines. You're getting rid of a gearbox that has a tendency to break, and a lot of O&M and a lot of having to be fixed has happened in Europe. So you're limiting that issue, and you're also getting more output from your generator. The other design is the drivetrain architecture, and the way the loads go on the turbine. I mean, you have a lighter nacelle than you would for the same size turbine. So that makes it easier to lift, it makes it easier to move, and it means if you have the less weight you have at the very top, the less weight you have to have all the way down, the less steel you use. So every ton of steel or ton of weight at the top of the nacelle that you eliminate has a multiplicative effect all the way down the turbine. These are some of the options we're looking at for foundations. The one on the bottom right is the one on the bottom right comes from a company called Keystone. It's a proven structure in the E&P industry for the gas and oil drilling industry. It's called a twisted jacket. And so what you see there is the water line. Then you go down to the water line, and you see that other layer below that is where the piles are driven. So a normal monopile, which a lot of people have talked about, is thick and gets pounded directly into the seafloor. Those, as you get into deeper water, use a lot of steel. They also require bigger hammers, which are louder and which have more impact on marine life as well. So you still do have to drive, but you're driving much smaller. You're driving much smaller piles in through it. And another thing that you can't see from here is that design is also they're much more standard pieces that can be serial manufactured. So there's embedded in that design is less steel, but it's also using some standard steel manufacturing techniques that lower the overall cost. But that would be kind of a normal install. You still would have to have a vessel, put that in, and then you'd put a turbine and tower on top of that. The one on the top left, it says Titan on there. That's a unique design. It's good for much deeper waters once you get over 30 meters. It basically is it would float out. You'd put the turbine fully on it. You float it out, and then you put it out, and then it just jacks up. So those legs that you see on the side would just extend all the way down, go on the bottom, and lift it up. It theoretically can be moved. So you theoretically, from decommissioning perspective, you could just jack it back out and tow it back out. Possibly from an O&M perspective, if you have a major issue, there's something wrong with the turbine where you can't just, most of these turbines have inbuilt cranes that can handle a lot of repairs, but if you have a major issue, it may be cheaper to actually, instead of mobilizing a ship that could cost you $500,000 a day, to jack that back out, tow it back into shore, fix it on shore, and bring it back out. And so it gives you the option. It's much more, although jackups like this for E&P platforms have been done before, doing this with a turbine would be a very unique, it has not been done to date. So that one has a bit more risk. The one on the bottom left is a gravity base with kind of a suction bucket. So instead of taking a monopile and pounding it in the ground, which is what standard installation techniques are, this one you put on the ground. You have to have the right type of soil, and you using suction to actually pull it down into the surface. So you're not being as violent when you're pounding it in. The opposite end of that is if you have too porous of a subsurface, too rocky, you can't actually get the suction to pull it in. It also hasn't been out in the water long enough for turbines of the size we're talking about. One of the things we're going through is a lot of the foundations people are looking at are because the standard turbine out there is a Siemens 3.6 turbine. Now everyone's looking at 6 megawatt turbines. They're significantly larger, and something like this, when you start to get in deeper water, may not be appropriate for it. But those are the three main ones we're looking at and comparing that to a standard monopile installation. Now, installation options are kind of tied to that. So the conventional jackup rig you see on the top left is where you take a jackup. It has an inbuilt crane, and you either have barges bringing all your pieces, or they come all out on that ship, and then someone's gonna have already put in the foundation. You put on the tower, you put on the nacelle, and then you put each of the blades on. You kind of compare that to the bottom right, or the one on the right, which is this is an install it's been done at least once, and where you do all your commissioning onshore. So instead of doing all this work offshore with all the vessels you'll need, all the people, with all the weather risk, you do your installation onshore, and you just take it out. You take it out and you drop it down into a pre-made foundation. Depending on what kind of foundation type you have, it has a lot of benefits in terms of, the more things you can do onshore you're talking a multiple, 2 or 3 or 5 times cheaper to do an onshore. More things you can do, kind of the general cascade is you want to do things in the factory. If you can't do them in the factory, you do them kind of in your staging site. If you can't do them in the staging site, you do them on water. And you want to push as much as you can back that chain where you're doing it where it's easier to do. So in this case, instead of commissioning and putting blades on water, you're going to do it and you can take it out. What you need, though, is a monstrous crane. And there's not a lot of ships that exist that can actually do that. I believe this is a 5 megawatt turbine. And I think you'd have to up that if you're talking about some of the sizes of turbines we're talking about. And the last is some of the foundations that are out there require ships specifically designed for that foundation. Our study isn't looking at those because we kind of feel that we're not going to have immediately enough volume to justify a self-designed ship. So some of these are unmanned ships that have foundations. They go out and they're specifically designed only for that and not useful for anything else. And so we looked at those and said some of them have promise, but we don't believe they'll be ready in the time frame that something would be installed in Virginia, and also require such a commitment that we think there's other things that will get you those cost reductions without having that much capital outlay. And I end with that. I mentioned the DOE technology demonstration projects. I think someone mentioned earlier, I think there were 30 responses. The DOE put out $180 million, which was a significant commitment. When they first talked about this, they had kind of a request for information on it, and one of our concerns is it wouldn't be a significant investment. It was actually, they're talking about $50 million per project. They kind of have they have a phased approach. They're going to initially select 5 projects. And you go through a year of, basically a little over a year of engineering, which DOE picks up about 80% of the cost as long as you stay under their budget. Although I think if you're really serious about it, you probably will spend more than that. And then they're going to down select to 3 projects that they intend to go forward with. And after that, when you start going into construction and operations, they pick up 50% of the tab for up to their $50 million number. That's pretty much all I have. I have some other slides on transmission. If people have questions, I'm happy to talk to them, but I think we need some time for questions.
I'll ask our panelists to come back up front. Really for Dane and John, the modeling is fantastic, and it really goes to Guy's point of getting more out of the same amount of steel. And so understanding where to locate turbines and how high to put them and specific site characterization is important, both from the standpoint of minimizing construction costs and maximizing performance. But is there a trade-off between getting it close enough and then accuracy and precision here, in the sense of there's not all on the onshore, there's a lot of terrain variation, there's trees, there's interference from different areas. Offshore, there is more of a homogeneous location. So is there less a need to be very site specific and micro siting of turbines versus onshore?
Well, I can't answer to that question specifically because Jay Titlow from WeatherFlow would definitely be able to answer this question better. But from during my conversations with him, he said that there were significant variations from site to site, and they varied. The wind speeds can vary just a couple of miles further off the coast, and your wind speed can drop. Or some of his results were as the height increased, wind speeds actually decreased. So it is an important factor to be able to map your resource as accurately as possible. At the same time, it does have to be cost effective. There's only so much you can do, and actually measuring the wind resource offshore is far more expensive than onshore. And
yeah, I think Brian makes a very good point. When all the years we've thought about and studied the wind resource on land, particularly in Virginia, it's no coincidence that the developers have been mostly interested in the higher elevations, the ridges, the knobs. These are the areas where the wind tends to blow much more strongly. So there is the terrain influence, and there are some areas If you were in the resource assessment session earlier, you heard some discussion about the complexity of the lands, not only in Virginia, but in other states around us as well. And we've done SODAR work with the folks who are looking out in western Rockingham County. Likewise, when we get off into the water, the terrain isn't an issue anymore. But one of the things to consider is that there are other influences, and particularly we have large bodies of mass that change temperature at different rates. And the Chesapeake Bay itself, the largest estuary in the country, has enormous influence on the wind resources. And so what we see as we proceed off the coast and into the waters is, and I mentioned this earlier, it's not just a uniform increase as we go farther or go higher. It's a lot more complex than that. So I think to answer the question, and I think Dane would agree with this, we really need more data. We can only go so far with the models, and the models become more reliable and robust if we had higher elevation data and it was more densely recorded.
Okay, so a couple good questions from our audience. We're going to get away from the technology aspect of this for a little bit, but which of the stakeholders, if any, show apprehension or opposition towards VCIRC's offshore wind farm location, and what are their concerns? I think maybe a general comment of, you know, Cape Wind ran into a lot of opposition from people, you know, having homes along the coast, looking at wind turbines and not wanting to see them. Are we running into that? Is VCIRC running into that same opposition, or are there other oppositions they're running into from fishermen or other stakeholders? And what have been their concerns, and how does that play into this?
Well, among the concerns that we've heard, I'd have to say the one that was cited most frequently is probably avian activity, and rightly so. I think most of you who are familiar with the area know that it's a very busy flyway. There are numerous breeds. There's a lot of activity, and I'm catching Carol's eye here. These issues came up during the RAP process, particularly when we were focused on the area of the bay and in the Eastern Peninsula and so on. So I think anyone who is going to engage in a development project is going to need to engage the conservation folks, the avian experts, and understand the nature of that activity and how it can, any impacts on avian life and activities can be minimized. Aside from that, I think, you know, we heard other concerns I mentioned before. Oyster beds is another issue, and there are other sensitivities on the subsurface. There are bound to be, and we didn't really explore this very deeply, but there are bound to be some concerns raised about aesthetic impacts, and we've got to be mindful of that as well. But at the end of the day, we just need to know what all the factors are and how we can best balance those.
Okay, question for Guy. Mr. Chapman. The Virginia energy law allows construction works in progress to be used for cost recovery of new renewable energy projects, including offshore, just as the CWIP is allowed for nuclear. Do you think that the authority is adequate to provide for financing of offshore wind in Virginia, or do you believe that other authority is needed to assure financing, i.e. to give Dominion the incentive to go forward on this? If so, what additional financing authority do you believe is needed?
Well, I think the current, in terms of, you know, CWIP and financing a facility, I think that construction work in progress. So one of the things that used to happen with rates is you'd go build a facility and you'd spend all your money building it. You get to the end of building it, and then you'd try to get it put in rates, and it caused a huge step change. And so suddenly there was a very large jump in rates, which could be, depending on time, very contentious. And so now the Virginia law says you get approval for your facility, and then as you start spending money building it, it slowly gets put in rates. And so there's not that big shock to the ratepayer, and there's also not a large risk premium of money that's potentially not recovered that a utility is spending. So it kind of matches what the dollars you're spending with the dollars you're recovering to minimize that outlay. That structure works really well for generation, regardless of what kind of generation you're going to build. And could you extend it earlier to do it for things that take a long time and have significant development costs, like offshore wind? You put offshore wind and nuclear probably in both in those areas. And up till now, we don't get recovery of anything that we're spending on development until we decide to build it. That's how that law is set. So once we've decided that it's going to be built and we take it to the commission says yes, then that law kicks in, the recovery kicks in. Changes in, so that is very adequate for financing any facility. Changing that is not going to really change the offshore wind gets built. It is more some of the stuff we talked about, getting it closer, more competitive, getting that premium over conventional generation down to a level that the constituents of Virginia would pay for, and you can get through a commission is the key, more so than changing that, because I think the current law is adequate for financing even something as large as an offshore wind facility.
We're just going to keep going here. We got a couple more questions. for Mr. Miles, if you considered the Gamesa site at least for a turbine test site at Cape Charles now that Gamesa is pulled out of Virginia, you might want to give a little background to that.
Okay, well, first of all, the background is that there was an effort underway by Gamesa to develop testing capabilities at one point offshore and on land in the area of Cape Charles to test their new technologies. That is probably many of you know is off the table for the time being anyway. I wasn't sure what the question was. What would? Okay. And that was not. And in fact, as we were not just embarking on this project, but before the proposals were approved and before we were funded and moving forward, we had some conversations about the Gamesa site. And quite frankly, what their intentions were to test their own technologies were not really consistent with the model we had in mind. We were looking more at the opportunity to facilitate testing and demonstration of not just one design, and this was not an industry-driven process. This was a publicly driven process meant to facilitate a later, hopefully private sector, maybe with federal investment project. But the message early on when Gamesa was active was this: we've got this under control. We're going to do this in a certain way that's consistent with our business model, because really they were trying to get it done quickly, and we didn't really have anything to offer at the time. Now, having said that, with Gamesa having at least appeared to have pulled out from this, there may be some value, particularly for the Cape Charles community, to looking at that site. Gamesa did considerable work and analysis, and I've got to think that if they were interested in enough to test a large turbine, that there might be a resource and an opportunity there, perhaps for a community scale project that would benefit the southern end of the peninsula.
I'll take this one, and Guy can tell me if I got it right. Mr. Chapman, this morning, Ms. Salud Gooden of Dominion stated that the land-based wind was not currently viable for Dominion, Virginia, because several factors, including the likely disapproval by the SEC under the RPS and low natural gas prices. Since offshore wind is more expensive to build than land-based wind, are there any reasons that you are more optimistic about the prospects for development of offshore wind by Dominion versus onshore wind? I think the answer there is it's very difficult to build 1,000, 2,000, 3,000 megawatts of wind onshore in Virginia. I mean, just look at the amount of opposition that's gone into building the projects around here. So to get any type of scaled renewable energy, that's where it's going to come from. It's going to come from our offshore resources. We just don't have the land. This is not Nevada in the sense we've got desert where nobody is. We've got people all over the place. So offshore wind is our renewable resource, and so from the standpoint of developing economies of scale and build, if we're going to get to a substantial portion of our generation source being renewable, that's where it's going to come from. So I don't know, guys, is that a fair point?
I'd say, remember, things change. If you would have looked at our IRP in 2004 and 2005, there wasn't as many combined cycles as there are now. Gas prices change, federal legislation changes, lots of things change. We will actively, if we were doing the lease blocks, we're going to actively develop them, because it's an option that, if things change, to try to catch up and try to be prepared for when gas prices go up, is going to be difficult to do. So all the renewables that we're looking at and developing, we're developing with the intention of building them, but we can't tell you, we can't tell you the the environment will be in terms of gas price and in terms of legislation at that time. So I think that's a major, you have to look back and say a lot of things have changed that may change the dynamic that makes us, when you take it to commission, may get a different answer 5 years from now.
And along those lines, I think there's another question, Guy, given what you say that the current cost of offshore wind is decreasing it by 25% will still put it way above the long-term LCOE of natural gas, so the cost of natural gas generation. So why is Dominion willing to commit $500,000 to buying the Virginia lease and at least 20 to 30 million more in studies during the preliminary 5-year lease? I think it's because it's an option payment, right?
I think it clearly falls into the fact that things may change, and you never know what generation resource is going to be the one that will make sense at any given time. And in terms of the ability to go execute this, you're going to have to spend significant amounts of money. You know, we've been developing a nuclear reactor for, I think it's over 10 years. And so I think that's representative of building those options, because we don't know which one will be the best option to execute for the ratepayer. Now, if you're an advocate, the bad thing is if you're an advocate of a specific technology. You know, we get people from solar or wind, different biomass, different gasification technologies. If you're an advocate of your technology, you're not thrilled with that answer, but it's the best answer over the long run, because you have the option ready to execute when that fuel changes, or when fracking suddenly can't happen, and we're exporting gas, and gas is at $8 because Japan needs it because it shut down its nuclear reactors. I don't know if that'll happen in 2 years. I don't know if it'll happen in 15 years, but that's an option that someone would have to be prepared for.
Question for Dane and John. What is WASP, and how does it extrapolate to hub height? I was wondering that too. And then a follow-on, kind of an interesting question. What are the innovations in blade design?
Well, WASP is industry standard software, and what WASP does, it takes your site-dependent data that you recorded from your Met Tower, and you generate a data set of site-independent data called a wind atlas. And then from that site-independent data set, you can generate a grid at, say, 80 meters of what your wind resource looks like based on that wind atlas. So the wind atlas would tell you, let's say, at 10 meters hub height, if the terrain has a roughness factor of 0.1, the wind speed is 5. And if those values change, if the roughness and height change, you'll get a different value. And then you can use that to generate a grid of wind values based on the actual map that you've constructed. I hope that explains.
So now in English, Dane's absolutely right, and I've been working with this a fair bit longer, so I've had the chance to talk about this a little bit more in layman's terms. And really what it is, it's an atmospheric model. It's taking the laws of physics that some of us have had the opportunity to study, and building the model. This is hard to explain. Building a model that looks at one point that's known. It's a reference point based on real data, and then applying the laws that govern the flow of a fluid, literally the air, and trying to predict what the flow is going to look like at another point in space at a given time or at a later time. And then doing that in a dynamic fashion. So when Dane talks about the wind atlas, what we're really doing is we're predicting the meteorology looking forward. Len, do you have a better description than that?
That's not the way dimension scale models work, and that sounds like an ill-posed problem.
I try to describe it more in generic terms, not precisely the way the WASP model works, because then it gets really complex.
Oh, okay. Because I do think the way you describe it is the way those types of models work.
Right.
It's not the way weather forecasts
Understood.
The weather forecast model has equations of conservation, mass, energy, momentum, and integrates them numerically. And,
Yeah, I didn't want to go there. Okay, thank you. There was another question about
turbine blade innovations, materials, self-dynamic adjustments and things. Are you studying that?
Yeah, somewhat. I mean, blades have come a long way. At one point in time, blades were made of wood and they were made of metal, and now they're made of composites. And what's, I think, really interesting now is that we're seeing blades that are longer, more slender. We try to make them lighter but stronger. And that ultimately, I think we'll see more and more designs that are actually responsive in shape. And so that they are going to be more able passively to respond to changes in conditions to optimize performance and conversion of energy.
And then the last question, I think, touches on, typically you have transmission as a whole nother track in one of these panels. And I'll put it over to Guy. I know Guy has some slides. I don't know if you want to get back up and do that because we're pushing on time. But I think some of the key points are talk a little bit about the Google transmission line, the Atlantic Wind Connection effectively. How does that play into Virginia specifically or not? And then number two, I think talk a little bit about AC versus DC. There's two main transmission types, and are there some real savings there, or is that just a different types of transmission, and there's really not benefits of either?
And I'll just point out our closing speaker after the next session is from Atlantic Wind Connection, so there's an opportunity to interact with her as well.
Yeah, I'll start with Atlantic Wind Connection. So how does that play into Virginia? That line comes, starts up in the Mid-Atlantic, up in New Jersey, comes to Maryland, hit Delaware, and then the last leg comes down here. It is a DC line, so a DC electricity. You have a long legs like we're talking about for that line. You get less losses. So when you send electricity through a line, you have losses. So that helps lower the losses. If they build it down here, would we consider connecting to it? Yes. It is of all the lengths of that line to get to a generation resource, this is the longest one coming down to Virginia. And so I think there's the concern about cost allocation is a big issue. There's also concern about what that does to effectively exporting power from our area potentially up north. So there's a long time. They have a lot of work to do before they are able to really come with a plan for when they'll be in the water and how they'll interconnect and what that will cost a generator. And at the time we take a look at that. We talk about AC and DC. If you're going to do a long line like that, it can make sense to do DC. Otherwise, you're doing alternating current lines. So out of your generator, you take your generators directly to a platform, and then you step it up in voltage, which means you step it up so it's a higher voltage, so you don't have as much losses, and you bring it to shore. If our wind energy area is 25 miles off of Virginia, at that distance, DC by itself doesn't make sense. You're seeing those in Europe when you start getting past. Some people say 40 miles, some people say 50 or more, but once you start getting past that, then you start seeing DC lines being a real option. And the only other thing I'll say about our transmission studies, which are publicly posted, and if you go to Dominion and just search for offshore wind transmission study, you'll get a link to it. One of the big issues is stranded cost. So if you know you're going to build your answer, and this is one of the big things with Atlantic Wind Connection, if you know you're going to build 3,000 megawatts and you know when you're going to build them and where you're going to build it, it's a lot easier to plan something like that. Stranded cost, some of the concerns are, if you only build 500 and you build that big line out there to Virginia, it's not going to be cheaper than just building directly into the coast. And so, that balance between risk and how much capital you put out is one of the ones that we came away from our transmission study with, because we looked at, could you build a 2,000 megawatt platform out there? And yeah, you could, but how long does it take you? There's actually a lot of capital carrying costs of having that out there, and then you have a single point of failure where your generation is potentially stranded if that single point of failure breaks. So some of those issues are things that you have to think about when you think about those big solutions.
Okay, well, I think that concludes, and thanks for our panelists. It was a great, interesting presentation. Thank you.